Yeah. Good evening, guys. Are you able to hear me?
Yes, sir.
So in this class, we will discuss about simple and compound microscope. Okay. So let's see what a simple microscope is all about. Right. So we are going to see what a simple microscope is. We are going to explain its working principle, and we are going to write the expressions for its magnifying power under two scenarios, where the final image is formed at the point called as least distance of distinction, and the second is when the point is at infinity. Okay. Basically, if you take a simple microscope is also called as a magnifying glass. It is basically just a convex lens of short focal length, and it is held very close to the eye. So what is it called? A simple microscope is also called as a magnifying glass. But what is it all about? It is a basic convex lens of short focal length, which is held close to the eye. Right? So if you observe, whenever you talk about any optical instrument, so whenever you talk about any optical instrument, remember that the final image formed is always virtual in nature. So final image formed will be virtual in nature. Okay. So generally, when I say a convex lens, right? So for a convex lens, let's first observe. If I take a convex lens, right, for which there is the principal axis and there is the optical center. If you have the focus here and center of curvature on the left of it, when the object is placed between the focus and the center of curvature, you can see that a ray considered parallel to the principal axis after reflection will pass through the focus on the other side, and the other ray through the optical center will travel without any deviation. So what will happen is these two refracted rays, do not have a provision to meet. Hence, when you extend them in the backward direction, they meet virtually somewhere over here. And this is one situation where it forms a virtual image. Okay. So what I'm trying to say is basically when you take the whole lens into consideration, whether you talk about convex or concave, so convex plus concave put together, right? You have a total of 8 ray diagrams, of which 3 are virtual. So in those 8 ray diagrams, you can see that in 3 ray diagrams you will get virtual image, right? Of which only one virtual image is magnified in nature. The one virtual image is magnified in nature. And then one virtual image is formed only due to a convex lens, and it is formed at the back of the lens itself. It is formed on the same side as that of the object itself. So am I clear with this point?
Yes, sir.
Am I clear with this? Okay. So having this point in mind, what we will do is we will try to understand the working principle of a simple microscope. So basically, image can be formed at two locations. What did I say? One of the locations is called least distance of distinction, and the other is called at infinity. Okay. So when the image is formed at least distance of distinction, even before I proceed, you need to understand what exactly is this least distance of so what is this least distance of distinction? So if you see this least distance of distinction, it is also called as near point. So near point means it is a point at which a naked eye can see an object comfortably. Okay. So that's what is given. See, since a normal eye can see an object clearly at the least distance of distinction, for a normal eyesight, d is equal to 25 centimeter. You would have learned about this near point in your 10th grade, right?
Yes.
Then, if you want the final image, if you want the final virtual image to be formed at the least distance of distinction, then what you will do is you will adjust the position in such a way that the image is formed at the least distance of distinction. Okay.
Yes.
So for which I will draw the ray diagram and show. So the one I drew it here is in such a way that if this distance is u, then the final image is formed at the least distance of distinction. Okay. Now see, let's say this is the height of the object and your eye is here. And you're looking at this object, let's say at an angle theta, or I'll call it as alpha. Okay. Then, when you're looking at this object initially without an optical instrument, so if you're looking at it without an optical instrument, then the first thing that you'll do is you'll ensure that the image is formed at the least distance of distinction. So you will ensure that it is formed at capital D. Okay. Then I can say tan alpha will be equal to H naught divided by D, which is approximated to alpha, which is H naught divided by D. Let this be equation number 1. Okay. Now see, if this is the height of the image, which is formed at the least distance of distribution, but with the help of an optical instrument. Then let's say the final image is subtending an angle beta at the eye. So what has happened? When you look at the height of the object with the naked eye without the help of an optical instrument, then the final image is formed at least distance of distinct vision, but the angle subtended by the object at the eye is going to be alpha. Whereas when you're looking at the final image with the help of optical instrument, it is beta. When this is the scenario, now observe, there is a concept called as magnifying power of an optical instrument. So it is defined like this. It is defined as the ratio of the angle subtended by the image to the angle subtended by the object. Okay. So if I call magnifying power as capital M, then the angle subtended by the image is going to be hi divided by d, and the angle subtended by the object is going to be h naught divided by d. So d and d will get cancelled. This will be equal to hi divided by h naught, which is actually equal to the linear magnification itself. Okay.
Yes, sir.
Okay. Now what I will do is I will apply the lens formula. When I apply the lens formula, I'll get something like this. 1 by v minus 1 by u is equal to 1 by f, which implies 1 by v is formed at minus d minus 1 by u is minus u is equal to 1 by focal length of a convex lens is positive. So which implies minus 1 by d plus 1 by u is equal to 1 by f. So multiply with d on both sides. So when you multiply with d on both sides, minus 1 plus d by u is equal to d by f, which implies d by u is equal to 1 plus d by f. But what is d by u? D by u is the linear magnification. So linear magnification will be equal to 1 plus d by f. But in this case, we know that linear magnification is numerically equal to angular magnification or magnifying power. Okay.
Yes.
The next point is what happens when the image is formed at infinity? So what happens when the image is formed at infinity? Let's see. So when I have a convex lens like this, optical center. So this is the focus. If I take a ray parallel to the principal axis, it passes through the focus on the other side. And through the optical center, it travels without any deviation. So if you observe, the final image is formed at infinity. So when the final image is formed at infinity, now what happens is, if you observe, this distance is smaller, right? This angle will be beta. So we already know that tan alpha is equal to h naught divided by u. But what is tan beta equal to? It is the same h naught divided by f. Right. So to be more specific, h naught divided by d. So magnifying power will be equal to alpha, beta divided by alpha. So beta is how much? H naught by f divided by alpha is h naught by d. So it will be d divided by f. But remember, d is negative because it is on the left hand side, and f is positive because the focal length of a convex lens is positive. So the magnifying power of a simple microscope when the image is formed at infinity is given as minus d divided by f. Done?
Yes, sir.
And we'll try out some problems based on this. So if you see the uses of simple microscope, watchmakers and jewelers use magnifying glass for having a magnified view of the small parts of watches and the fine jewelry work. In magnifying the printed letters in a book, textures of fibers or threads of cloth, engravings. So if you want to magnify anything on a printed book or something, then you use something like, then you use a magnifying glass. Similarly, magnifying glass is also used in science laboratories for reading vernier scales. So if you want to see any reading more precisely, then you can use this simple microscope. Okay. So based on this, there is an example given here. There is a thin convex lens of focal length 5 centimeter, which is used in a simple microscope by a person with normal near point of 25 centimeter. So there is a thin convex lens of focal length 5 centimeter, which is used as a simple microscope by a person with normal near point. What is the magnifying power of the microscope? So magnifying power is 1 plus d by f. 1 plus d is how much? 25 divided by focal length is 5. So that is going to be 6. If you observe here, I didn't use sign convention while solving the problem. Is it clear? So I didn't use sign convention while I solved the problem. Reason being,
Already.
the reason, because this is a specific case. This is the only case where this formula is applicable. There is not a generalized formula like a mirror formula. For mirror, you have 8 ray diagrams. So you need to use the sign convention. Whereas here you don't have 8 ray diagrams. You have only 1. So that is why you're not using the sign convention while solving the problem. Okay.
Yes, sir.
So example 119. If you see, a simple microscope is a combination of two lenses in contact of powers 15 diopter and plus 5 diopter. Calculate the magnifying power of the microscope. So what is the equivalent power? So equivalent power is going to be plus 20 diopter. Calculate the magnifying power of the microscope. So how to calculate it? So if power is 20 diopter, what is going to be the focal length? Focal length is 1 by 20. 1 by 20 is going to be 0.05 meter or 5 centimeter. Right? So where is the image formed? The image is formed at least distance of distinction. In that case, magnifying power is 1 plus d divided by f. So it is going to be 1 plus d is how much? 25. D is 25 divided by 5, which is going to be 6. The answer is 6. Example 120. If an object is seen through a simple microscope of power 10 diopter, so power is equal to 10 diopter, focal length will be how much? 1 by 10, which is 0.01 meter, or which will also become 10 centimeter. Right? Where should the object be placed so as to produce the maximum angular magnification? So what is the value of capital M? So they are asking maximum angular magnification. So maximum angular magnification is how much? Then the image is formed at, I'll give you two options, you tell me. Infinity or capital D. So maximum linear magnification means where should the image be formed? Should it be formed at infinity or capital D? Sorry? it should be formed at capital D, because when the image is formed at capital D, the magnification is 1 by D by 1 plus D by F. Whereas the image, when the image is formed at infinity, it is only D by F. Is the point clear?
Yes, sir.
1 plus is obviously going to be 25 centimeter. Focal length is how much? It is 10 centimeters. So 1 plus 2.5 is 3.5 is going to be the magnification. So what is they ask? They ask object distance. Sir. Object distance to 1 by V minus 1 by U is equal to 1 by F. So 1 by V in this case is minus 25. Here I need to use. In the formula, magnification formula you will not use, but in the mirror formula you need to use. Minus 1 divided by U is how much? U is what you need to find, is equal to 1 by F. F is plus 10. So 1 by U is equal to minus 1 by 25 minus 1 by 10. How much is going to be the answer? Minus 10 minus 25 divided by 250 minus 35 divided by 250, or U is equal to minus 250 divided by 35 or minus 50 divided by 7. So 50 divided by 7 is 7.1 centimeter. Is it clear?
Yes, sir.
So next one is a compound microscope. So when you talk about a compound microscope, we can say these things. So basically, compound microscope is also an optical device which is used to see magnified images of tiny objects. Then what is the difference between a simple and a compound microscope? As the name suggests, compound microscope is a combination of lens. So when you look at simple microscope was only having one convex lens, whereas when you talk about a compound microscope, it has two lenses which are combined, right? So it consists of two convex lenses of short focal length arranged coaxially at the ends of two sliding metal tubes. So when you have two sliding metal tubes, and if the convex lenses are of short focal length, then they are arranged coaxially in such a way that they have a pinion and a rack arrangement, so they have a rack and a pinion arrangement so that they are able to get adjusted among themselves. So here we told about two convex lenses, right? So out of which one of the convex lenses is called objective. So what do you mean by objective here? So objective is the convex lens of very short focal length and small aperture. And where is it positioned? It is positioned near the object that is to be magnified. So since it is placed closer to the object, it is called as objective. Similarly, you have an eyepiece, or you have something called as an ocular. So what is an eyepiece? It is a convex lens of comparatively larger focal length and larger aperture than the objective. So where is it positioned? It is positioned near the eye for viewing the final image. So that is why it's called as eyepiece. Okay. Now the question is, when the final image, again I told you, right, when you're talking about optical instrument, there are two positions where the images are formed. One of the positions is the least distance of distinction, and the other position is obviously at the infinity, right? So when the final image is formed at the least distance of distinction, then you can say that the object AB is viewed at a distance u0. So let me explain this concept. So you have an objective which is placed near the object, and you have an eyepiece which is placed closer to the eye. If you see this diagram, when the object AB is placed, okay, when the object AB is placed closer to the objective, then what happens is, when you consider a ray parallel to the principal axis, okay, when the ray is considered parallel to the principal axis, after reflection, it passes through the focus, and if you observe, the final image is formed beyond the focus of the eyepiece, that is between the focus and the optical center of the eyepiece, in such a way that this image has got magnified already once. So the magnified image due to the first lens will act as the object for the second lens, as a result of which it is again magnified and the final image is formed at this point. Is this point clear?
Yes, sir.
Right. Now, if you see, if this is the height of the object h, then this will be the height of the first image, which I'll call it as h dash, and the height of the final image will be h double dash, in such a way that without the help of optical instrument, when you see, the object is subtending an angle of alpha near the eye, and if you see the same thing with the help of an optical instrument, it is subtending an angle beta at the eyepiece. So if you observe the magnifying power is beta divided by alpha, and if you observe what is beta, beta is h double dash divided by d, and alpha is going to be h divided by d. This and this will get cancelled. This will be h double dash divided by h, which is also linear magnification. So in the case of a compound microscope as well, what will you get is the magnifying power will be equal to the linear magnification. Right? So this h double dash by h can also be written as h double dash divided by h dash into h dash divided by h. So h double dash divided by h dash is the magnification produced due to the eyepiece into h dash divided by h is the magnification produced due to the objective. So to put it in simple terms, the combined magnification which is produced by both the lenses put together will be the product of the magnification of objective and the magnification of eyepiece. And to put it in simple terms, magnification of objective is V0 divided by U0, because it is a basic convex lens. And magnification produced due to the eyepiece would be 1 plus D divided by Fe. So then the combined magnification that is produced will be M0 into Me, which is V0 divided by U0 into 1 plus D divided by Fe. And this is what we call it as the final magnification that is produced, or the magnifying power of a compound microscope. Is this point clear?
Yes.
The next one is when the final image is formed at infinity. So when the final image is formed at infinity, now what will happen is m naught will be equal to the same thing, v naught divided by u naught, and me will change to d divided by f, because eyepiece is acting like a simple microscope only. So the linear magnification in this case will be equal to m naught into me, or I'll put it as v naught divided by u naught into d divided by fe. Is it clear, guys?
Yes, sir.
So, okay. So based on this, we will try to solve a problem. And before that, I just want to introduce another term which is called as capital L, which is generally called as tube length. So tube length is basically the distance that is there between the objective and the eyepiece. And what we have done is we have written V naught here, right? Instead of V naught, it is sometimes approximated to the tube length itself, because the distances are slightly smaller, that the approximation is very well held good. Okay. So when this is the case, okay, so magnification can also be written as L divided by F naught into D by Fe. Just a minute, I have a call to attend. Did you guys understand this? Now listen. Yes, let's try to solve this problem. When you have a compound microscope with an objective of 1 centimeter, actually it is not an, it is centimeter focal length, and an eyepiece of 2 centimeter focal length which has a tube length of 20 centimeters. So L is equal to 20 centimeter. Calculate the magnifying power of the microscope if the final image is formed at the near point. So what is the formula for magnifying power? Magnifying power will be L divided by F naught into 1 plus D by Fe. So L is how much? 20 divided by F naught is how much?
1 centimeter.
Into 1 plus
25 by 2.
25 by 2.
2.
That's right. So 20 into 1 plus 12.5. So 20 into 13.5, which is going to give you 270. So 270 will be the answer. So you are given two converging lenses of focal length 1.25 centimeter and 5 centimeter to design a compound microscope. So it is desired to have a magnification of 30. Find out the separation between the objective and the eyepiece. So magnification is L divided by F naught into 1 plus D by Fe. So L is how much? L is what we need to find. That is a tube length, right? Divided by F naught is how much? So 1.25 and 5, which one has shorter wavelength? Objective or eyepiece?
Objective.
So it is 1.25 into 1 plus D euro. How much is D?
25.
25 divided by Fe is 5 and magnification expected is 30. Will you be able to calculate this? 1.25 is 5 by 4. So with the help of it, calculate the value of L. I hope you are able to understand, right?
Yes, sir.
Yes, sir. Good. So 30th, 129th problem. The focal length of the eyepiece and the objective of a compound microscope are 5 centimeter and 1 centimeter respectively. And the length of the tube is 20 centimeter. Calculate the magnifying power of the microscope when the final image is formed at infinity. The value of least distance of distinction is 25 centimeter. So focal length of eyepiece is 5 centimeter. Focal length of objective is 1 centimeter. And the length of the tube is 20 centimeter. Calculate the magnifying power of the microscope. So M is equal to L divided by F naught into 1 plus D by Fe. So when the final image is formed at infinity, infinity means D divided by Fe. L is how much? 20 divided by F naught is how much?
1 centimeter.
1 into D is how much?
25.
25. Fe is
5.
5. So 5 means it comes out to be 100. But I made a mistake. Answer is not 100. The focal length of the eyepiece, length of calculate the magnifying. So when the final image is formed at infinity, okay, when the final image is formed at infinity, magnifying power will be V naught divided by U naught into D divided by Fe. So how to calculate V naught? So if you observe, this is 20. If this is V naught, okay, then this point is exactly the focus of eyepiece, which is 5. So 20 minus 5 is going to be 15. So V naught is actually 15 divided by U naught is how much? Okay. So then I will use 1 by V minus 1 by U is equal to 1 by F. So I'll use a naught. So 1 by V naught, that is 1 by 15 minus 1 by U naught is equal to 1 by F naught. F naught is how much? 1.
1, sir.
So 1 by U naught is equal to 1 by 15 minus 1. So minus 14 divided by 15 is 1 by U naught. Upper U naught will be minus 15 by 14 centimeter. Okay. Then magnifying power will be V naught divided by U naught into D divided by FE. V naught 15, U naught is minus 15 by 14 into D is 25, FE is 1. FE is 5, no?
5.
So it goes 5 times, cancel it, it will be minus 70. So the magnification produced in this scenario is going to be minus 70, and the negative sign indicates that it is an inverted image. Okay.
Yes.
So this is all about simple and compound microscope. Okay. This is all about a simple and compound microscope. About telescope, we'll discuss tomorrow. Okay. So tomorrow also mostly it will be online only because there is painting work going on in the academy. So mostly it will be online only. Okay.
Okay.
Yeah. That's it. I'll see you.
Okay,
sir. Bye.
Thank you, sir.
Thank you, sir.